On June 13, 1944, on a narrow road outside the Norman village of Villers-Bocage, the morning was quiet, hedgerows on both sides, birdsong, the low murmur of engines in the distance. Then a single German tank emerged from the tree line, 57 tons of steel, its Maybach engine turning at idle, the exhaust note low and sustained. Inside a British Cromwell, a gunner acquired the target and fired. At that range, a 75mm round, aimed at the Tiger's front plate, should have been lethal. The shell struck, deflected, a metallic clang audible to both crews, and tumbled clear. The tank's commander was Michael Wittmann, SS Obersturmführer, 29 years old. He would later be known as the Black Baron. What he did in Tiger 007 that morning became one of the most debated individual engagements in military history. Now he drove straight into the British column, alone. The British 7th Armored Division, the Desert Rats, veterans of North Africa who had fought Rommel himself, were extended along a narrow village street in a tight, exposed column. Wittmann drove through them, not around them. In approximately 15 minutes, 11 to 14 tanks were burning, 13 carriers destroyed, and 2 anti-tank guns wrecked in the road. The entire British advance halted, not repelled, not slowed, but stopped outright. The men inside those Cromwells and Shermans were not cowards, and their guns were not weak by the standards of the time. At combat range, against 80 to 110 millimeters of sloped, hardened steel, shells did not penetrate. British commanders afterward struggled to describe the engagement, and there was no tactical answer available at those angles and that distance. The disparity in protection was not a gap, it was an absolute barrier. Tiger 007 was not, however, the most extreme product of German tank engineering. It was neither the largest nor the heaviest result of a design doctrine that had concluded, in the higher offices of the German military-industrial complex, that sheer scale was itself the decisive weapon, that a vehicle made sufficiently heavy, sufficiently armored, and sufficiently powerful would impose its will on any engagement it entered. The furthest expression of that doctrine was a vehicle so heavy it collapsed every bridge it approached, ruptured the road surfaces beneath its tracks, and moved so slowly that the war had nearly ended before it could fire a single shot in combat. On the question Allied commanders were confronting by the summer of 1944, and that historians have returned to at length since, remains instructive. How a program of such engineering ambition produced so little decisive effect on the outcome of the war. Germany's problem was not a shortage of brilliant engineers. The problem was that those engineers were answering the wrong question. By 1942, the war had fundamentally changed shape. The Blitzkrieg, armor and aircraft moving in overwhelming, coordinated speed, had taken France in 6 weeks and driven deep into Soviet territory before the first Russian winter arrived. By that winter, the momentum had broken. The front now stretched from the Norwegian coast to the Caucasus Mountains. Supply lines were beginning to strain, and within the German command structure, a logic was establishing itself, quietly at first, then comprehensively, that if a single Tiger could stop an entire British column, something larger could stop the entire war. Ferdinand Porsche was not a soldier or a strategist. He was a designer, arguably the finest automotive engineer in Europe at that moment. In 1942, he received a commission that no grounded, rational man should have accepted without serious pause. Build a tank so large, so heavily armored, and so formidable in its firepower that it would render every Allied vehicle obsolete in a single encounter. Not a tank as an instrument of maneuver or combined arms doctrine. A tank as a declaration of German engineering will. The result was the Panzerkampfwagen VIII Maus. And the name Maus, applied to something that weighed 188 metric tons, is perhaps the clearest indication that, at some critical stage in this process, the program had lost its connection to the war actually being fought on the ground. 188 metric tons. Heavier than 2 fully loaded Boeing 737 passenger aircraft combined. Its main armament, A 128mm KWK-44 gun with a barrel stretching over 7 meters could destroy any Allied tank at a combat range of 3,500 meters. Its turret frontal armor was 220 millimeters of hardened steel. No Allied anti-tank weapon deployed anywhere in the European theater could defeat it from the front at any practical engagement distance. At 188 tons, the Maus would collapse virtually every bridge in Western Europe the moment its tracks touched them. On the engineering solution to this, and this was not satire, but the formally approved, seriously documented operational plan, was that the Maus would ford rivers by submerging itself. The crew would drive along the actual riverbed using a snorkel breathing system, while a second Maus positioned on the bank supplied electrical power to the submerged vehicle through a thick copper cable stretched across the water. Two of the most complex and expensive fighting machines ever produced, required to operate in synchronized underwater tandem simply to cross a river, while a standard Sherman crossed a pontoon bridge in 90 seconds and continued moving without interruption. Two prototypes were completed. Neither ever fired a shot in combat. Neither crossed a river of any kind. The Maus was not an isolated failure contained to one program, and it was a symptom, the most visible peak of a doctrine that had already worked its way into the German war machine from within. The Wunderwaffe philosophy, the belief that one final, sufficiently decisive weapon could reverse a war of sustained industrial attrition, was a dead end constructed by brilliant men who had stopped thinking in systems and started thinking in monuments. The resources consumed by programs like the Maus were not theoretical costs. They were real tungsten, copper, and chromium drawn directly from frontline production. They were tens of thousands of engineering hours no longer available to vehicles that were actually functioning, fighting, and winning engagements. Even the proven Tiger I, the weapon that had performed at Villers-Bocage and across the Eastern Front, was already consuming itself with maintenance demands that no army could sustain indefinitely. Every hour of combat operation required approximately 10 hours of intensive, specialized maintenance from trained crews with the correct equipment. This was not a minor inefficiency. It meant regiments of Tigers spending more days behind the lines being rebuilt than they spent in action. The Schachtellaufwerk interleaved road wheel system, elegant on an engineering drawing, a serious liability in the field, packed so thoroughly with frozen Eastern Front mud that the entire running gear could seize solid overnight. Replacing a single failed inner wheel required mechanics to first remove as many as 9 outer wheels. In temperatures of -30°C, in darkness, with artillery falling at irregular intervals. By 1944, 35% of all Tiger II losses were not battle damage. They were self-destruction, crews detonating their own vehicles because fuel was exhausted or a transmission had failed beyond roadside repair capacity, and the Allied advance was moving faster than any German recovery vehicle could respond. Germany had built the most individually formidable armored force in the history of warfare. It was quietly consuming itself from within. Meanwhile, in Detroit, a fundamentally different approach was producing a fundamentally different result. The question driving it was not how to build the best tank, but how to build the one that was always present. And the Sherman was not a great tank in the way the Tiger was great, not by the criteria the field used to measure greatness in 1944, which centered on armor thickness, kill range, and the mathematics of penetration versus protection. British crews called it the Tommy Cooker. German tank crews called it the Ronson, after an American cigarette lighter brand whose advertising slogan at the time was "Lights first time, every time." That reputation was real, and the fires it described were real. Men killed inside burning vehicles in the hedgerows of Normandy and the valleys of Italy. Acknowledging this, honestly, is the necessary starting point for understanding what followed. The fire problem was identified, diagnosed, and substantially corrected. Not in a post-war review, not in a leisurely peacetime engineering assessment, but while the war was actively being fought, and while men were still dying inside the machines. The primary cause, once identified, was straightforward. Ammunition stored in the fighting compartment's sidewall sponsons directly exposed to shell fragment penetration. The engineering response was equally direct. Relocate the ammunition bins and surround them with water-jacketed wet stowage, a system in which rounds sat encased in a liquid-filled jacket that suppressed internal fires long enough for crews to react and escape. On M4A176W variants equipped with this system, the catastrophic fire rate dropped by approximately 3/4. Most historians of armored warfare know this. Many general audiences do not, and that gap is where the Ronson label has persisted for 8 decades. That the fix was developed matters. That it was deployed while the war was ongoing is the more significant fact. America's industrial system could receive battlefield feedback from France, process it through an engineering revision, and deliver the corrected vehicle on production lines in Ohio within months. That responsiveness is not a footnote to the Sherman story. It is the Sherman story in concentrated form. Between 1942 and 1945, American factories produced 49,234 Shermans. The complete production total of the Tiger I across the entire duration of the war was 1,347 vehicles, a ratio of more than 30-to-1. A Sherman cost between $33,000 and $55,000 to build. A Tiger I cost the wartime equivalent of $100,000 to $120,000, factoring in precision alloys, specialist tooling, and hand-fitted assembly. The construction of a single Tiger I consumed approximately 300,000 man-hours of labor. A Sherman required 48,000, meaning that for the labor cost of one Tiger, the Detroit industrial complex could produce 6 Shermans. In the same month Germany finished a production batch of Tigers, American output had already exceeded Germany's entire annual Tiger production. Quantity without supply chain coherence is only a statistic. The deeper question is how the Shermans were built, and what that method made possible in the field. German wartime factories operated on a system of continuous running changes, modifications applied on the shop floor, hour by hour, incorporating the latest engineering directive before the previous one had fully propagated through the system. The result was that no 2 Tigers were quite identical. A replacement component machined one week might not seat correctly in a vehicle produced the week before, because both had been built by different workers following divergent specifications that had not yet been formally reconciled. German field mechanics were not just repairing tanks. They were improvising repairs on machines that had quietly become unique objects in a war that punished uniqueness. American production operated on standardized block upgrades, the M4A1, the M4A2, the M4A3. Each variant was fully specified before production began, built identically across multiple factories simultaneously. Chrysler in Detroit, the Fisher Tank Division in Grand Blanc, the Baldwin Locomotive Works in Pennsylvania, and released as a uniform, interchangeable unit. And a transmission produced by Chrysler in Michigan would fit a Sherman built by a completely separate manufacturer in California, without modification, without measurement, without question. This was not engineering convenience. It was the foundational discipline that made the entire Allied logistics system functional across 2 oceans. When a Sherman lost a transmission in France, the replacement had already crossed the Atlantic weeks before anyone knew which vehicle would need it. The consequence registered as a single unglamorous figure that changed the arithmetic of the war: operational readiness rate. Research by armor historian Steven Zaloga, drawing on unit records from both sides, established that Sherman-equipped formations maintained approximately 85% operational readiness throughout sustained campaigns. Our German Panther and Tiger formations during the same period rarely kept 50% of their authorized vehicle strength combat-ready at any given moment. Half of Germany's most capable tanks were always broken, always behind the line, always waiting in a maintenance queue that never fully cleared. A theoretically perfect tank, immobilized 200 miles from the front, has a combat value of 0. That is not a rhetorical observation. It is the defining equation of the tank war in Western Europe. The 5 Shermans to kill 1 Tiger ratio, repeated in post-war memoirs, printed in histories, dramatized in film, requires direct examination. It originated primarily from German crew accounts written after the war from prison camps, and from a well-documented wartime phenomenon historians call Tiger terror. For Allied crews were so conditioned to fear the Tiger that they misidentified Panzer IVs and stowage assault guns as Tigers in engagement reports with considerable regularity, and after-action statistics accumulated phantom Tigers as a result. When analysts like Zaloga returned to cross-referenced records, confirmed wreckage surveys, serial numbers, and calibrated kill claims from both sides, the 5-to-1 ratio did not hold. The actual decisive variable in most lethal tank engagements, regardless of which vehicles were present, was the same one it has been in ground combat throughout history. Who identified whom first, and who held tactical initiative in that moment? On turret traverse speed alone, a detail rarely mentioned in popular comparisons, the Sherman held a decisive mechanical advantage. Its electrically driven turret could complete a 360-degree rotation in under 15 seconds. The Tiger's turret, driven by an engine-dependent hydraulic system that reverted to hand crank in any emergency, required nearly a full minute for the same movement. In the close-range, fast-moving terrain of the Villers-Bocage, where engagements were measured in dozens of meters rather than hundreds, the tank capable of responding to a flank threat in 10 seconds versus 60 was not at a disadvantage. It was at a lethal one. The Sherman's dimensional constraints, the properties frequently cited as evidence of insufficient ambition, were deliberate engineering decisions, not failures of imagination. Its width was held below a threshold defined by Allied port crane lift capacities. Its weight was capped to match U.S. railcar specifications. The Tiger I required a specialized set of narrowed transport tracks simply to fit on a German rail flat car, adding several days of logistical preparation before any major redeployment could begin. The Sherman disembarked from a Liberty ship and was driving within the hour. When the Firefly entered service, the Sherman hull rearmed with the British 17-pounder anti-tank gun, the vehicle German crews had previously dismissed could penetrate Tiger frontal armor at standard combat ranges. German tank commanders received explicit written orders to prioritize destroying Sherman Fireflies above all other targets on the battlefield. That is not the operational protocol of an army dismissing an inferior opponent. It is the protocol of an army that has identified something it cannot afford to ignore. Note what kept the Sherman mechanically reliable, what allowed it to remain operational where the Tiger sat broken, leads to one of the most improbable pieces of engineering improvisation in the history of mechanized warfare. In 1941, the American tank program was accelerating across every front, contracts being signed, factories being converted, workers being retrained from peacetime production, but no engine was available in sufficient quantities to power the machines being built. The Wright R-975, a 9-cylinder air-cooled radial originally designed for light aircraft, had been adapted as the Sherman's primary power plant in early configurations. It worked adequately, provisionally, but never in quantities sufficient to match the production ambitions being laid out in Washington. But the Wright engine was competing directly with aircraft programs for its own production capacity, and aircraft were not going to lose that competition. A conventional engineering organization facing this constraint would have done what convention requires: commission a bespoke tank engine design, assign a team, and wait the 12 to 18 months needed to develop, test, and certify something new. Chrysler Corporation's engineering team, working in the autumn of 1941, made a different choice. They looked at what was already in production, already at scale, already accumulating real-world reliability data on civilian roads across America. They took 5 existing 6-cylinder passenger car engines and geared them together around a single central output shaft in a radial configuration, 30 cylinders in 5 banks of 6, a driving 1 output shaft. The result was the Chrysler A57 Multibank, and it had absolutely no engineering right to work as well as it did. The specifications, on paper, were not embarrassing. Combined displacement across the 5 banks totaled 1,255 cubic inches, 20.5 liters, greater than the combined engine displacement of 3 modern full-size pickup trucks. Output ranged from 370 to 445 horsepower, depending on the configuration variant. The engine weighed over 5,000 pounds and occupied the Sherman's rear compartment with a density of components: 10 camshafts, 30 pistons, 5 initially separate cooling circuits, a central gear reduction assembly of considerable mechanical complexity that, to anyone unfamiliar with its origins, looked less like a military power plant and more like something assembled under considerable time pressure. The first reasonable question any engineer would ask, examining the A57 disassembled, was how it managed not to destroy itself on first startup. It ran, and it kept running. The A57 gave the Sherman a top road speed of over 25 miles per hour, faster than any German heavy tank deployed in Western Europe. The Tiger I, despite its 700 horsepower Maybach V-12, managed approximately 23 miles per hour on a good road surface, and had a transmission so fragile under the torque load of 57 tons that drivers received formal instructions not to exceed certain gear selections without specific cause. The Tiger II, heavier still, was slower. The Maus, the apex of German heavy tank engineering, moved at 13 kilometers per hour on paved road. The Sherman, powered by 5 rearranged passenger car engines, was faster than all of them. Speed was not, however, the significant variable. The significant variable was what happened when the engine began to fail. The A57's architecture, 5 independent cylinder banks, mechanically coupled but operationally separable, meant that losing any individual bank did not disable the vehicle. A Sherman whose engine had lost 3 of 5 cylinder banks could still move under its own power. Reduced speed, reduced power, but moving, rolling toward a maintenance depot under its own momentum rather than sitting immobilized in a forward area, waiting for recovery assets that might or might not arrive. A Tiger I with a single failed transmission, not 3/5 of its engine, just one component in its sole drivetrain, was immediately and completely immobilized. The crew would wait for recovery, or they would set the fuses and walk away. Redundancy as a design principle is not complicated. It is the oldest reliability engineering principle in existence. What made the A57 notable was not that Chrysler's engineers understood it. It was that they arrived at it through pragmatic expedience, using 5 passenger car engines because there was no time to design something purpose-built. The engineering insight and the practical constraint reached the same result from entirely different starting points. The spare parts advantage was the most consequential of all. Because each of the 5 banks descended directly from Chrysler's civilian passenger car engine line, the internal components, pistons, piston rings, valve seats, cam followers, water pump seals, were not exotic items produced from specialty alloys available only through the wartime strategic materials chain. They were, in the most literal sense, the same parts already stocked in the same warehouses already supplying American cars and trucks across the United States and Britain. A field mechanic with a requisition form could source a 57 replacement components through the same logistics pipeline that delivered oil filters to American family sedans. The supply chain was already mature, already distributed, already tested by millions of vehicle miles of civilian use before the war began. A German mechanics in the field inhabited a categorically different situation. The Maybach HL230 V12, the engine powering the Tiger I, Tiger II, and Panther, was precision machined to tolerances that required chromium and tungsten alloys Germany was critically short of by mid-1944. Beyond the material shortage, the continuous running change production philosophy had created a compounding incompatibility problem. Parts ordered from the latest factory output often would not physically seat in vehicles manufactured even a few months earlier, because both had been built to slightly divergent specifications by different workers following different directives. And the solution adopted by German maintenance units, systematically cannibalizing functional newer vehicles to supply parts for operational older ones, was not a command failure or logistical oversight. It was the only mathematically coherent response to a parts ecosystem that had been allowed to diverge from itself. Chrysler ran the A57 through a formal endurance test before field deployment, 400 hours of continuous operation, representing over 4,000 miles of simulated use. It passed. The Maybach HL230, under actual battlefield conditions, was logging significant mechanical failures at around the 100-hour mark with regularity, in vehicles operated by experienced crews, maintained by skilled mechanics, following prescribed service schedules. The Shermans improvised, cobbled together, a 5-passenger car engines-in-a-box power plant outran Germany's finest precision engineering by a factor of 4 in sustained operational endurance. The maintenance ecosystem around the Sherman compounded this advantage at every level of the logistics chain. The transmission was housed in a cast front case bolted to the hull. A trained crew with standard field tools could unbolt the case and drop the entire transmission assembly without crane equipment or depot facilities. A standardized replacement unit could be installed and the vehicle returned to operational status in a matter of hours. The same failure on a Tiger I required either a full maintenance depot with overhead lifting capacity or a decision to abandon the vehicle entirely. There was no workable middle option in a forward area. The United States Army institutionalized vehicle recovery as a combat function. The M32 tank recovery vehicle, a Sherman hull converted for battlefield retrieval, equipped with an A-frame crane, a heavy winch, and towing gear rated for the Sherman's full weight, was deployed in sufficient numbers that a damaged Sherman could be pulled back from a forward position and handed to a maintenance team the same day. German recovery assets existed, but never at the systemic scale needed to match the rate of frontline vehicle losses in sustained offensive operations. Over a 90-day campaign, the compounding arithmetic was straightforward. A German panzer division fielding 100 tanks could expect 40 to 50 operationally ready vehicles at any given moment. Say an American armored division fielding 100 Shermans could reliably count on 80 to 85. Across months of continuous offensive operations through France, Belgium, and into Germany itself, multiplied across dozens of divisions on a front stretching hundreds of miles. That gap was an industrial sentence from which German armor could not recover. Germany built the finest 12-cylinder tank engine in the world. It was never reliably present when it was needed. America built 5-passenger car engines into one improbable machine. It was always there. All of these numbers, the 49,000 vehicles, the 30 cylinders, the 85% readiness rate, remain abstractions until placed in the hands of real soldiers, on a real battlefield. In a real moment where the difference between a tank that starts and one that does not determines whether a town falls or a line holds. The clearest illustration is what happened to the man who, for one afternoon in Normandy, had made the entire Allied command believe the Tiger was unstoppable 3 months later, almost to the day. On August 8, 1944, during Operation Totalize near Sinto, France, Michael Wittmann was moving with his company along the road to Falaise. 3 months had passed since Villers-Bocage. He was 29 years old, credited with 138 confirmed tank kills, the most decorated tank commander in the German military, and had become, in the compressed mythology of a 3-year war, something approaching legend, the Black Baron, the man who had stopped an entire division with a single tank and 15 minutes of nerve. That morning, it ended in seconds. Wittmann's Tiger 007 moved into what post-war analysis would reconstruct as a fire sack, a coordinated engagement geometry in which multiple Allied tanks positioned at different angles fired simultaneously at the same vehicle from directions it could not face at once. The Tiger's defensive logic: rotate toward the threat, present the armored front, engage one enemy at a time, had no answer for this. No single vehicle, however heavily armored, can face every direction simultaneously. The fire sack removed the only defensive advantage a stationary heavy target possesses. Tiger 007 took a penetrating hit to the left rear hull, the thinnest armor. The ammunition detonated. The turret separated from the hull. So all 5 crew members were killed instantly. The most decorated tank commander in the German military was gone in the time it takes a projectile to cross 100 meters of open ground. The question of who fired the killing shot remains genuinely unresolved. Sergeant Joe Ekins, a gunner in a Sherman Firefly of the 1st Northamptonshire Yeomanry, has the strongest documentary case. The 4th Canadian Medium Regiment's artillery also carries a credible evidentiary claim. Historians have spent decades sorting through unit logs, trajectory analysis, and eyewitness accounts that contradict one another in the way that all battlefield testimony does. The identity of the shooter is not the significant detail. What matters is the nature of the weapon. It was not a secret counter-tank system or a desperate last-resort measure, or it was a standard Allied vehicle, a modified Sherman or a Canadian field gun, performing its assigned function on an ordinary Tuesday in August, operated by men who were where they needed to be because their equipment had put them there and kept them running while Wittmann's army was counting its maintenance hours. Wittmann was not defeated by a superior machine. He was defeated by a system, one that was always present. That system had been grinding through the German order of battle since Normandy began and would not stop. German tank crews of this period, in letters home and in later testimony, described the Sherman not with contempt, but with something closer to dread. And the dread was not of its gun or its armor. It was of its numbers, its inexhaustible, industrially sustained presence. For every Sherman that burned on a hillside, 3 more appeared on the road the next morning. For every Tiger lost to combat damage or mechanical failure, there was no replacement waiting. German production could not generate them fast enough. German logistics could not fuel the ones it had. German maintenance could not keep the ones it fueled operational long enough to matter. By the spring of 1945, Sherman columns were moving through the streets of German cities. Ordinary men in ordinary machines, exhaust trailing in the cold morning air, track links clattering over the cobblestones the German formations had marched across in confident ceremony just 3 years before. At the Kummersdorf proving ground south of Berlin, advancing Soviet troops found the 2 Maus prototypes. One had been partially destroyed by retreating German engineers, a demolition charge placed, with some apparent haste, in the engine compartment. The other was a burned-out hull. Together, they represented 376 metric tons of steel, thousands of engineering hours, a substantial fraction of Germany's dwindling reserves of precision alloys, and the concentrated ambition of an entire design philosophy. They had never crossed a river. They had never engaged an enemy vehicle. They had tested at Kummersdorf, consumed fuel, broken their drivetrains, and waited. The war ended before the engagement they were designed for could be arranged. Today, 1 Maus, reassembled from components of both prototypes, is on display at the Kubinka Tank Museum outside Moscow. It is the only one that exists. And visitors stand beneath it and photograph a machine that never mattered, preserved in steel because it was too large and too expensive to discard. The placard describes its specifications in the past tense, a monument to the distance between what can be imagined and what can be sustained. The M4 Sherman served with the armed forces of dozens of nations through the 1950s, the 1960s, and into the 1970s. Some variants remained in active operational service in South America into the 1980s and beyond, 4 decades after the war that produced them, still traversing terrain on the same operational philosophy that had crossed the English Channel in a landing craft and fought north to the German border. Still, in the most literal sense, running. The war was not won by the perfect machine. It was won by the one that kept running. Germany built the heaviest, most armored, most individually powerful expression of tank design the century had yet produced. It never moved fast enough or far enough or reliably enough to change the outcome of a single engagement that mattered. America built the machine that was always there, morning after morning, mile after mile, through the hedgerows of Normandy, across the winter mud of the Ardennes, and into the rubble of Berlin, not because it was perfect, because it worked, because when it broke, it could be fixed, because when it was destroyed, it was replaced, because the industrial system behind it understood a truth that no amount of engineering genius could substitute for. A weapon that shows up is worth 10 that don't.